You click full screen.
Yeah. Full screen. It's, yeah, I know it's not loading.
So it's stuck.
It's up. Hopefully we're good. Is that working?
No,
I'll see. Click on focus, yeah. Okay. Click the focus. Oh, can you click on the slides in focus? Now it does? Okay. Yeah.
Yeah, yeah.
So welcome to what will be the last CAMS colloquium of this academic year, but we will of course have more interesting things next academic year. And we're very pleased to welcome, in some sense, welcome back Jacob Bedrossian, who we knew when he was a graduate student at UCLA. Now he is a full professor at UCLA, and we're very happy to see him again. And he will talk to us on nonlinear dynamics in stochastic systems. Thank you, Jacob.
Okay, yeah, thanks a lot. It's nice to be back. Wish I had visited sooner, but it's been really busy. So, okay, so it's a suitably vague title, so obviously it's not as general as that. So I'll talk about, and this includes a lot of joint work with a lot of collaborators. I'll point out which joint works. Probably not all of them will actually appear. Probably no, I think they all appear. Oh, okay, so what is the okay, so what is the motivation, at least for the work? So not all of the work will actually have something to do directly with the Navier-Stokes equations, but it's all somewhat motivated by these equations. So here, for those of you who aren't familiar with the equations, U is a vector. This set of equations is basically force equals mass times acceleration. So this is the acceleration part, these two terms here. And this U dot grad U looks like a transport term because it's basically describing the fact that fluid particles will move with the fluid itself. So this is why the acceleration comes out like this. Then the two sort of intrinsic forces are this viscosity force. So this is a parameter nu. And this is basically friction that layers of fluid will feel when they slide past one another. So this will cause momentum to diffuse through the fluid. This pressure force is something that enforces the divergence free constraint, which says that when you squish out a fluid, it tends to squish out the sides as opposed to just compress. The parameter nu is called the kinematic viscosity or inverse Reynolds number, depending on the units that you choose. It will come up very rarely in this particular talk, but just for future reference, because you know the divergence, if you know the curl, then at least if you're in a simple domain like Rn or the torus, then you can recover the velocity by solving a div curl system. But even better, it turns out that this curl, called the vorticity in fluid mechanics, solves this beautiful transport-like equation. So this kind of Lie bracket looking thing is exactly the way to consider conservative transport of vectors in 3 dimensions. And in 2 dimensions, it reduces to a scalar. So there we just call it a scalar. Basically, it reduces to a conservative scalar transport. Okay, so this talk is concerned with a dynamics called turbulence. So let's look at this slide first. So this, obviously, we're all familiar with such a picture, just smoke coming out of a smokestack. But if you stare closely at it, you can see that the fluid is active on a lot of different scales. So obviously, it has large scale structure, but it has extremely small scale structures and everything in between. So it's not like a homogenization problem where it has one small scale and one large scale or something like this. It's sort of spread out through all scales, up until I don't remember the dissipative scale, maybe a millimeter or a couple of millimeters or something in this kind of fluid. Other thing you might recognize with turbulence is that every specific realization looks different, and no matter how much you try to control for that, you won't be able to. So this cloud will not look exactly the same, no matter how many times you rerun the experiment. On the other hand, they all kind of look the same, in some sense or another, right? And so that's what we want to get at. is some kind of statistical universality. Or, why do all smokestacks basically look the same, even though they all look different at the same time? And so what's happening over here on this slide, let me draw the axes. So this is what's called a power spectrum. So it's a log-log plot, and on this axis, it's log of the frequency. So this is low frequencies, this goes to high frequencies. And on this side, it's log of the basically time average of the energy. So I'll explain, basically think of this as a long time average of the energy at that frequency. And what you're looking at is the output of a physical experiment. So two realizations of a similar experiment. They have like an airfoil, and they're flowing air past, and they're looking at the wake behind the airfoil. And one experiment, they sort of put little thingy-majigs on the wing, and the other they don't. Okay, so the black line is the standard airfoil, and this other thing is where they kind of mess up the large-scale structure of the fluid. And you can see that while the large scales look totally different, the small scales look basically the same. The only difference is multiplicative offset. It's kind of like the total energy that they have. So what you expect, so Kolmogorov predicted a particular power spectrum, doesn't really matter for the purpose of this talk, but there's a particular spectrum that's supposed to be essentially universal across all realizations of fluids. We don't know, there's no proof of that or anything, but that's the idea. So we want to understand this, this kind of phenomenon. It's not specific to 2D to 3D fluids, it's not even specific to fluid mechanics. So 2D turbulence is actually ironically more complicated in some ways than 3D, but it also comes up in plasmas and atmospheric ocean sciences and dispersive equations and things like that. But it looks different in all of the systems, where some things look the same and some things look different. Okay, so I want to study this kind of phenomenon in some sense the most classical setting, which is a statistical steady setting, where I want to set up the experiment, like for example, flow over an airfoil. I want to set up the experiment and first send time to infinity and then send the parameter nu to 0. So first I'm sending time to infinity and letting it kind of settle into a statistical steady state. And what I want, the ultimate goal of the program is to provide, mathematical theorems that match the predictions of physicists and engineers. So they all have predictions about what what this plot is supposed to look like where this drop off is supposed to be, what the slope of this is supposed to be, but we don't have any theorems to that effect. Okay, and I want to study this in the case of random forcing. So there's many reasons why this is useful. One basic thing that the qualitative theory, like the existence of things we want to take the limit of, that at least is known if your forcing is random or stochastic, whereas if your forcing is deterministic, even that is not known. So at least you have qualitative theory, like you have invariant measures that you can study. And I'm going to be using dynamical systems methods, which are really only robust for random dynamical systems, in a sense. So what kind of canonical model am I thinking about? So let's just think simply stochastic Navier-Stokes in a torus, and let's not deal with the boundary. And I'll generalize this parameter. So m is bigger than or equal to 1. If m is strictly bigger than 1, it's called hyperviscosity. It's useful for computational purposes, but anyway, I'll explain why I want to keep that parameter general. So these statistics are not believed to depend on that parameter, except for where this occurs, the dissipative scale. Nobody knows that for sure. It's just a conjecture. For some things that I'm going to be talking about, we need stochastic forcing, and other things we don't. Roughly speaking, stochastic forcing is simpler. So that means white in time, and I want at least 1,000 times differentiable in space. So if you apply very rough in space stochastic forcing, it messes up the theory and you don't get the same answer. Okay, so you want kind of sufficiently smooth in space forcing, and white in time is the simplest. So the qualitative theory of this equation is very well understood, or I mean, it matches the deterministic theory. So in 2 dimensions, you have global apposedness of smooth solutions as long as this parameter is bigger than or equal to 1. And in 3D, you have global apposedness as long as this parameter is bigger than 5/4. You can also construct a weak solution theory, just like in the deterministic case. And I don't know if there might be even more general weak solution theory, but I don't know. And so you have, you know, this is a perfectly well-posed SPD. No problems at all. So let's say that we're in one of the settings where we do have well-posedness. And then in that case, you can define it, it's associated with a Markov process. So you have a Markov transition kernel that tells you the, you know, the probability of finding your solution in some state given its initial condition. And you use that to define two Markov semigroups. So this is an evolution on observables. So think of phi as like a measurement, like the total kinetic energy, something like this. So this gives you the expectation of the kinetic energy if you know the initial condition. This is an evolution on probability measures. What it basically tells you that if you randomize the initial condition with mu, you know, with some law mu, then the law of the solution at a future time will be given by P star. So it's an evolution on ensembles. Now, if you know deterministic fluid mechanics, you know that the first thing you learn is the energy identity. So if you carry out that calculation for stochastic fluids, the simplest version of that calculation gives you this. So the expected kinetic energy is balanced by the expectation of the energy dissipation plus the energy input plus the initial condition. And what's nice about stochastic forcing is that the energy input is known. So it's T times a number, just an external constant you can fix. That's one of the conveniences of stochastic forcing. You know how much energy is actually being applied to your fluid. It doesn't depend on the state of the fluid, interestingly enough. At least in expectation, I should say. So then if you divide by time, you see that the time averaged kinetic energy dissipation is bounded, which means basically that on average, your solution stays in a compact set. And it's relatively easy to prove that you can pass the limit and construct a stationary measure. So a fixed point of PT star mu equals mu. So that is saying that if you randomize the initial condition with that law, the law does not change. The solutions are of course flapping around or whatever, right? But the law isn't changing. So think of like, you know, water flowing over a stone in a river. So that's essentially statistically stationary. And you also know that the energy, because where else, what else could happen? The energy dissipation, the long time average of the energy dissipation will equal the energy input. So what else could happen? So this is just true. So the energy dissipation is just equal. Sorry, this number epsilon that was named by Kolmogorov. It's not my fault. But yes, for some reason chose epsilon to be like basically an order 1 number, like 12. But yes, so the energy dissipation just immediately balances this energy input. But I should mention, this is the only a priori estimate we know that's uniform and nu. Well, it's not uniform and nu. So as you send nu to 0, you don't really get that much information. But on the other hand, this is the only thing we know. So after many decades of research. Okay. Moreover, so that we have existence of something we want to study, this stationary measure. And in fact, it's very easy to, as long as we're on the torus, it's very easy, not easy. It's well understood how to prove that these measures are unique. No, it's not easy at all if you know how to write this paper, but it's known. So, you know, mathematicians always take everything that known goes in the easy bin, right? So, right, so these measures are unique. And so there's a unique long-term statistics. So almost every initial condition will, the time average statistics will converge to these ensemble statistics. So that's what physicists want. When they say ergodic, they mean ensemble average equals time average. And that is actually true here. Right? So I would say this is maybe the fundamental reason why, well, not the fundamental, one of the many reasons why random dynamics kind of works better than deterministic dynamics. Even in the case of non-well-posed solutions, when you just have weak solutions, you can still construct a statistical stationary weak solution theory, stuff like that. So even in the case of 3D Navier-Stokes with the true dissipation, you still do have natural objects to study in the inviscid limit. Nu to 0 is called the inviscid limit. It's not as nice. Maybe there's some works that there prove uniqueness in some kind of in-law sense, but you know, pathwise you won't have uniqueness. So it's a little bit more subtle. Any questions so far? This is just on the qualitative. So now, for every fixed viscosity parameter, we have something to study. So there's one more thing that we want to introduce, which is there's something really fundamental to turbulence, which is that if you rerun the same experiment, you don't get the same answer. So the reason for that is chaos. So the simplest measure of chaos, one of the simplest measures of chaos is something called the Lyapunov exponent. So imagine I have just for a second, just an abstract dynamical system on some phase space. And I take the derivative with respect to the initial condition, and I want to see if this derivative grows exponentially or not. So if that derivative grows exponentially, then that means a small change in the initial condition makes an exponentially large change in the trajectory, at least infinitesimally. In an infinitesimal sense, this is true. And so, if you're talking about an ODE on a compact manifold, that's as chaotic as you can get, or that's the largest gradient growth you can get. So, so basically you want to ask, when is this positive, and is it positive for sort of almost every initial condition in some sense? Right? And it's extremely, extremely hard to check this for any existing deterministic system. And I'll explain a little bit why that's the case. Even though almost every system, vaguely like a fluid, is chaotic if the damping is weak enough. We observe it. We don't have theorems about that. Well, a few theorems about that, but very little, right? So it's a little bit frustrating because you see it all the time in nature, but it's very hard to actually check. The only deterministic system which is known for either like very low dimensional systems that can be checked with a really complicated computer system proof, or systems which are, well, to call them trivial kind of makes it sound like those proofs are easy. But from a physical standpoint, they're somewhat trivial systems. Okay, so in fluid mechanics, there's actually two notions of chaos that are studied by physicists. So one notion of chaos is actually the simplest one to think about is if you have a particle moving in the fluid, like think of like a dust particle in the room. The question is, one question would be if I make a small change to that dust particle's initial condition, does that trajectory change dramatically? Right. So that's looking at the solution to this ODE. So this is the velocity field, and you just look at how a particle moves in this ODE. So this is just this weird notation is just parameterizing it by time, the noise path, so the realization of the noise, and the initial condition of the velocity field. So for every realization of the noise and every initial condition of the velocity, I get a different map on the torus. It's called the Lagrangian flow map. So one notion of chaos is whether or not the Lagrangian flow map is chaotic. So whether or not small changes in the initial particle position create large changes in the particle trajectory. A completely unrelated notion, a priori unrelated notion, is a small change in the initial configuration of the velocity field creates a large change in the velocity field at a future time. This would be like, more related to like the limits of weather prediction and stuff like that, where small changes in the state of the atmosphere create large changes in the future. A priori, they're completely unrelated. It's easy to come up with artificial examples which have this notion of chaos, but not this one, and vice versa. So a priori, they're not really directly connected. Okay, so what would a mathematical theory of turbulence look like? And I'll just say this in the 3D case because ironically, it's simpler. So one thing is you expect that both of these Lagrangian Lyapunov exponents are positive if the damping is weak. And there are predictions in the physics literature about how quickly they diverge as nu goes to zero. So you actually expect them to go to infinity as you send nu to zero. What do you expect? And there's precise predictions about exactly how fast they're supposed to diverge. Not theorems, obviously, no close to that. Another thing is something called anomalous dissipation. So let's explain it with this picture again. So what's happening in this picture? So this is, again, we have no theorems about this. Energy is basically being input at large scales. And we expect that the nonlinear dynamics of the fluid is stirring it all up. Oops. And sending it to smaller and smaller scales, where here it's dissipating. And so we expect a sort of constant flux of energy from large scales to small scales. So if you go back to the energy balance, and instead of just looking at time derivative of the L2 norm, you look at the time derivative of just the energy in this is a frequency projection to the first capital N frequencies. You just look at this kind of Lewis-Paley projection. What you get is the nonlinear term now looks like that, something like this. This vanished, This vanishes if you send n to infinity, but for any fixed n, it's just a number. And then you have the energy dissipation at that scale. And then you have the energy input. Up to that scale at least. So this is the nonlinear energy flux through scale n. This is how much energy is moving from large scales to small scales. So you expect actually as nu goes to 0, you expect that somehow this term vanishes, right? And you get that this term balances this term. So that's what the notion of anomalous dissipation would be. That the energy flux is basically you have a constant flux of energy from large scales to small scales.
Question.
Yes.
Is that the calculation over there, is that the expected value?
Oh, yes, yeah. If you don't put expected value, then you have another term.
Yeah.
Yeah. Yes, so you can see actually, yeah, so that statement only involves expectation. Yeah. Of course, one could also ask, like, do you actually have bounded kinetic energy as nu goes to 0? So are you actually dissipating energy fast enough for the L2 norm actually to remain bounded? Remember, that's not known. We have no idea. That's a pretty deep statement. Yes.
So say you're taking nu to 0, how would that graph change?
Oh, yeah. So basically this guy is going to go off to infinity. Yeah. So this is called the Kolmogorov scale. It's predicted, we don't know. And the physicists are not really in complete agreement. Should be about that in 3 dimensions. And then you can ask a bunch of more complicated questions like, indeed, what is the power spectrum? So how much energy in a given frequency shell are you actually going to see? Where is this Q? So that's asking where is this number? Like where is this line? What is this slope? And then you can ask even more complicated questions. And physicists like to ask these questions. Yeah. So basically, any question that you can find in the physics literature, pretty much any question you find in the physics literature about statistically steady turbulence, you can phrase as a mathematically rigorous conjecture. So it's not a question of what do we prove? The question is, how do we prove anything? Right. Okay, so we wanted to start with something extremely easy because we didn't know anything about turbulence. So this grew out from basically a reading course we ran where we tried to read some physics books on turbulence and then we read some papers on stochastic Navier-Stokes and tried to just put them together. So we see from this energy flux balance that if you could somehow fix n and send nu to 0 and just erase this term, you would have something like anomalous dissipation. Okay, but Kolmogorov was working in the 40s, and he said he probably knew this, roughly speaking, but this would have been extremely hard to measure in the 40s. So he actually sat down and figured out how to rewrite essentially the energy flux in a way that could be measured. So the only thing that they could really easily measure in 1941 was called the longitudinal increments. So he actually figured out that the cube of this longitudinal increment should be about -4/5 epsilon L in here, in this intermediate range. So this is what's now known as the 4/5 law. And so what we're able to do is prove that you don't need any hypotheses other than this extremely weak a priori estimate. And later, sort of former student at UMD also got the sharp, improved this to the sharp answer, which is if you fix n and then send nu to 0, you get 0. Then you get this 4/5 law. So this is like an averaged version of this one. And importantly, there's some details about this fact that that this line goes to infinity. We don't have a prediction about where this line goes, how fast it goes, but it has to go to infinity. In some sense. Maybe we can talk later about the exact ordering of these limits, but these are the correct ordering, I claim. It's the correct ordering that describes a range of universality that's really stretches from order 1 to all the way to infinity. Okay, so this is actually not that hard of a theorem to prove, but it's at least a nice sufficient condition. So basically, if you can break the scaling of the kinetic energy, then you can prove this, then you can prove the 4/5 law. So all you have to do is slightly improve the known a priori estimate. So we know that this quantity is bounded, but you expect it to go to 0. Basically, so if you
put any absolute values, like there's some cancellation going on possibly.
here,
Yeah, because there is a sign, the pseudo temp is a sign.
yes, it's definitely signed. It's definitely signed. 4/5 law is definitely signed.
Cancellations, or there's no cancellation?
There is expected to be cancellations. There's a really interesting paper by Theo where he talks about like under what conditions would the 4/5 law give you some kind of regularity under some kind of statistical isotropy conditions and stuff like that. It's a really cool paper. Yeah. Oh, sorry. Right. So then after that, we decided, okay, what can we do? Can we prove anything stronger? So the first thing we decided to do was study Lagrangian chaos because we felt correctly that that should be one of the easier things to study. So what we're able to prove is that for stochastic Navier-Stokes, at least if you're in kind of a well-posed situation, for all values of the Reynolds number, there exists a deterministic number lambda, which is positive such that this holds. So basically you have Lagrangian chaos, essentially unconditionally. With no quantitative estimate, as it depends on nu, of course. Well, not of course, but pretty much of course. Yes, but it is Lagrangian chaotic. And it's very important to understand that this limit holds almost surely. So every single realization will see this. This isn't some kind of average sense. You really, it really is chaotic. It's not, yeah, does that make sense? Yeah. Oops, keeps going the wrong way. Okay, so I'll talk a little bit about how we prove that theorem, but then basically what we wanted to do, we wanted to see if there was a system simple enough, but still a fluid system for which we could get this kind of picture. So we knew that we weren't going to be able to jump directly to Navier-Stokes, but so we thought about the following system, which is a lot simpler. So you take Navier-Stokes, let's say we're in two dimensions, and you fix nu as a parameter. You fix it. And then you dump a passive scalar in. So this is a model for something like a very small salinity variation or very small temperature variation, where the variations are so small that they don't go back and affect the fluid. Right, so you can just think of this temperature variation as just being dragged along by the fluid. So it's just advected, and then you have some dissipation and you have some external source. And then you want to send this parameter to 0, kappa to 0. So the limit when the diffusivity of the scalar vanishes. So this is a particular case of what's called passive scalar turbulence. And so I'm not going to talk about the Kolmogorov 4/5 law for passive scalar turbulence. I mean, it's more interesting because we now have the actual power spectrum. So I'll explain that. So that took significantly more work to get the power spectrum. But what is the prediction? So this is kind of an analog of this picture. So this is the dotted line is what we expect from the fluid in 3 dimensions at least. The black line is what we expect from the passive scalar. And this is actually observed in physical experiments. You just go out into the ocean and dump a sensor off the side of your boat and measure it. You will see pictures that look very much like this. Very much like this cartoon. And so basically what happens is that there's some range of scales where the 2 power spectra are the same. We have no idea how to prove that. I'm not prediction about that. But after, if kappa is really, really very small, then the fluid might look smooth at these small scales, but the scalar does not yet. And the scalar will come out with this -1 slope. So the way the physicists scale it is they put this k to the dimension here. So the slope -1 tells you that heuristically at least, this is like 1/k to the dimension. I mean, Batchelor's heuristic did not predict it. It doesn't make a prediction pointwise in k, but you observe that it holds pointwise in k or something. We don't know how to prove that it's pointwise in k, as you'll see. But right, so that's what the prediction is. So what we're able to prove is that that's true in a cumulative sense. So if you sum the energy less than scale n, it scales like that. So you get this log. It's really important that this holds for some n naught, which is independent of kappa. These constants are independent of kappa. So nothing depends on kappa except, we know basically we know exactly the dependence on kappa here. So that's really important that nothing else depends on kappa. Essentially, so we don't know how n naught depends on nu, which is just another way of saying we don't know where this line is. But we know that at some point, if you make kappa much smaller, if you really fix nu and send kappa to 0, this line is somewhere. And beyond that line, you get -1. And you can even fill out a couple of other things on that big slide of what we want to prove for turbulence. So you can pass the implicit limit and construct kind of like anomalously dissipating distributions of scalars and stuff like that. Anyway, right. So then after that, we decided we wanted to try and do Navier-Stokes. We quickly realized we were not going to be able to just jump directly to Navier-Stokes still. And we realized that actually a lot of the questions that we wanted to prove, like chaos, like Eulerian chaos, we realized that we didn't have any idea how to do that even for finite dimensional approximations. And so we started to make a more detailed study of what happens for even finite dimensional approximations of Navier-Stokes. And I know that that's not really going to be like turbulence, but if you can't understand that case in a very detailed manner, you probably won't be able to understand the infinite dimensional case either. And so that's what we've been sort of consumed with the last couple of years, is just thinking about, can we even do any of these things analogously in finite dimensions? So one of the things that we were able to do, so let me just define a finite dimensional truncation for Navier-Stokes. So this is just in 2D. I think you can do the 3D case as well, but I've yet to recruit a grad student who is motivated enough to do that. Let's say, so as you'll see, well, I won't really explain, but there's a step in the proof that uses a computer-assisted proof that's somewhat tedious. So if you want to check 96 polynomials in Maple, come talk to me. Okay, so in 2 dimensions, so W, the vorticity, is a scalar. We can expand it as a Fourier series. And then you can write the equations like this. And here I've rescaled so that the dissipation and the forcing actually match. That is okay to do in finite dimensions. It's not a good thing to do in infinite dimensions. We can discuss later why that's the case. But in finite dimensions, you can, I mean, of course, you can always do this rescaling, but trust me, you don't want to do it in infinite dimensions. Yeah. Or anyway, we can talk later. But in 5 dimensions, yeah. Then, so the nonlinearity is completely encoded in this particular, these coefficients, which crucially for the proof is a rational polynomial. Okay, and then basically all you do is you just cut off this infinite set of SDEs somewhere. We cut it off in a square. So you just cut it off, and then for every capital N, you have the finite dimensional SDE. Nice SDE. So what we're able to prove is that for every fixed dimension bigger than 396, as long as you're forcing enough modes like 4 or 5 that create some kind of specific pattern, then you have chaos as long as nu is sufficiently small. So here you do need nu small, and it's not too difficult to prove that if nu is large, then this Lyapunov exponent is actually negative. That's actually the easy case. So there you definitely need nu small because it's false.
Large compared to what?
To some number. Right? I mean,
To the
okay.
to the forcing?
Right.
The
Well, I mean, right.
size of the forcing, or
So if you're just talking, if you're trying to find the nu for which this is negative, then it's basically just large compared to this alpha and beta. And then it's easy to figure out. This sufficiently small is hard to figure out. Because this sufficiently large is probably even independent of dimension. So that's true in infinite dimensions as well. But the other thing, obviously, we don't know in infinite dimensions. So here, this may depend on dimension. Basically, yeah. And we have this, sorry, this epsilon is new. That's new. There's no epsilon in this problem. Yeah. Right. So this is not expected to be sharp at all, but it's something. Okay, so how does this work? So if we pretend for a second that, so now I'm going to do something confusing, where I'm going to rewrite this SDE. So here I have an SDE. So what is the structure of an ST? We have some kind of vector field, right? And then I have some other vector fields times Brownian motions. And this is additive noise. These alphas and betas, they don't depend on W. So we don't need to care about Ito versus Truncations or whatever. And so I'm going to rewrite that system in this abstract form. Right? So this contains the deterministic Navier-Stokes equations. And these are all the vector fields that I'm forcing the system with. So I've numbered x0 is the deterministic piece, 1 through r is the forcing directions. And I can think of my system as living on Rn. If you deal with the reality constraints and stuff like that, you can rewrite it on Rn if you want. So right now I'm just thinking abstractly, essentially. So then the Markov semigroups that I introduced at the beginning of the talk, they blessedly solve PDEs. So these things are called generators. I'm using these vector fields to also denote directional derivatives. This is kind of standard notation in geometry, but nowhere else, essentially. Yeah, it's only confusing the first 16 or 17 times you look at it. But yeah, so this is like, x naught is basically this vector field dot gradient. So if you had no noise, for example, this is just the method of characteristics. So the Markov semigroups are just the extension of the method of characteristics from transport equations to SD, from ODEs to SDEs. So it's the method of characteristics for SDEs. Which is great because I actually do PDEs. I don't do probability or dynamical systems. Well, I do now, but that's not where I grew up, so to speak. Okay, so let's talk about trying to estimate Lyapunov exponents. Why is it hard? So what you're trying to do, right, if you think about this, if you take the derivative with respect to the initial condition, you just get this ODE. So J is a matrix or whatever. And so you have this ODE, and you're just asking, when do the solutions to this ODE grow exponentially or not? Seems like a simple question, right? So first of all, right, we know from our ODE class that time-dependent ODEs, even linear ones like this one, can be extremely hard to solve. Right? The only case that's easy, quote unquote, is if this doesn't depend on time, and then the Jordan canonical form gives you some kind of classification. So interestingly, when this thing is an ergodic process, you can also use, there's an ergodic theory analog, essentially, of spectral theory called the multiplicative ergodic theorem, which is an extremely beautiful theorem, the real depth and beauty of which is not on the slide. So the simplest part of the theorem is that there exists Lyapunov exponents. And in fact, they're deterministic under the assumptions, I'm sweeping some assumptions under the rug. In particular, I'm using uniqueness of the stationary measure and some properties at infinity, that doesn't grow, doesn't have weird properties at infinity. So there are assumptions. So I'm just, So there exists a top Lyapunov exponent so that this limit holds almost surely. And there exists, although there exists actually a whole spectrum of Lyapunov exponents, just like eigenvalues. And, but I only need to care about two of them, the top one and the sort of total one, which is the asymptotic compression or expansion of Lebesgue measure in phase space. So both of these exist and they hold almost surely. So at the ODE level, the existence of these things is a well-known thing. It's completely solved a long time ago. And so just proving the existence of Lyapunov exponents is not, again, it's easy in the sense that it's done already. So why, but estimating them is still hard. So it's something that at least my collaborator calls cone twisting. And I think the easiest toy model for this is IID determinant one matrices. So imagine I'm pulling determinant one matrices out of a hat and just multiplying them together. And I'm asking, when does this random matrix multiplication grow exponentially or not? If you think about the way this random ODE works, it's not a bad toy model. You're just removing the correlations. There's a couple examples easy to check that this lambda is 0. So one is just a random rotation, obviously that has no growth. Another one is essentially you can think of this like a random shearing. So it's like going, stretching the vector like this. This grows, but it doesn't grow exponentially. The other case, I think it's most interesting to think about this version of this case, where imagine this P is like 0.999999999, right? So almost every matrix you pull is going to be this one. So you're going to stretch the x-axis exponentially and compress the y-axis. So great, so it looks like you're growing exponentially. But if you wait, a couple of trillion years or whatever, you can get this matrix and you're going to flip the x-axis and the y-axis. And then for a couple of trillion years, you're going to be stuck getting this matrix again. And so all that growth that you built up is now going to start getting undone and reversed. And so no matter what P is, except, if it's 0 or 1, lambda is 0. Okay. And so if you think about this, so the expanding and contracting cones got twisted back in on themselves. And if you think about this for a deterministic system, that means in order to prove that Lyapunov exponent is positive, you need to know the entire time history, the entire trajectory, everything about the trajectory to time going to infinity. And that would be pretty tricky if you're looking at a system that's supposed to be chaotic. So obviously it's extremely hard to prove positively Lyapunov exponents, even for extremely simple systems. So there's a really interesting conjecture in deterministic dynamics called the standard map conjecture, which basically has one of the most trivial 2x2 systems imaginable, and we have no idea how to prove that it's chaotic.
Does someone have to let Ling Feng in?
Okay, so why, oh no. Did I break everything? Okay, so a really cool theorem, which is basically that in the random case, with I'm talking about random matrices, these are the only examples which lambda is 0. If you determine a 1, very important. So you have to do a volume preserving transformation for this to work. But essentially, this beautiful theorem, which says that if lambda is 0, then one of the following two holds. Either there's a deterministic inner product for which you're almost surely in isometry. So one single inner product that's deterministic, and you're almost surely in isometry with respect to that one inner product. Or there's exactly 1 or exactly 2 lines fixed again deterministically. Anything else, and you have chaos for volume preserving systems. And you can, there are many enhancements and versions of this. It's of course not restricted to 2 dimensions. It's not restricted to IID matrices. You can do it for things like random ODEs and apply it to SDEs. And you can use it to prove chaos. So this is actually how we prove Lagrangian chaos. We basically use some kind of partially infinite dimensional extension of Furstenberg's ideas. Okay, that doesn't work for Eulerian chaos because it's very important that you're volume preserving. So this is it's a beautiful proof, but it is a contradiction argument that doesn't give you any quantitative information. So it doesn't, if you make an epsilon perturbation, you can't, or normally you can't kind of get quantitative information except under certain settings, of which dissipative systems do not hold, at least our setting. So, right, so you need something more quantitative. So here's what we did. So the proof of the theorem is very dependent on something called the projective process. So here you take a vector, you apply the Jacobian matrix to the vector, and then you normalize it and you snap it back to the sphere. Or you identify, you probably should identify the antipodal points of the sphere and just think about it as a line through the origin. So what is important about this vector VT? It's going to tip in the direction of expansion. So if the matrix dpht is expanding in one direction exponentially, VT is going to tip in that direction exponentially fast. So imagine that you're looking at this ODE. Well, why am I doing like that? Why don't I just think? Imagine you're looking at a kind of hyperbolic saddle like this, right? Then if you look at the projectivization of this, you'll get a line that is going to tip exponentially fast into the x-axis. And so this point is like an unstable repeller, and this point is like a stable attractor. So directions of expansion now become exponential attractors on the projective piece. And so what you do is you lift the SDE to the sphere bundle or the projective bundle, and you can actually, it's still an SDE, it's a formula for the lift. And so you have an SDE on a more complicated manifold, and it has Markov processes and stuff like that. And so you could then study the stationary measure of that process. That's really important. And so for example, the dimension being bigger than 396 in our theorem, that came from the second paper where Sam and I proved that this lifted guy has a unique stationary measure for Galerkin Navier-Stokes. But but it's a computer-assisted proof where we have to choose. We didn't really obsess about what dimension was high enough. We just wanted a computer-assisted proof that worked in all sufficiently high dimensions. Right. And in fact, you can prove that for Navier-Stokes, for example, that the solution, that the stationary measure of this process is almost absolutely continuous with respect to like Lebesgue measure on this manifold, and strictly positive, which is not so unusual for SDEs. And that measure, I'm going to denote the density F, and that F solves a PDE, solves the Kolmogorov equation on the manifold. That's very important. So it kind of gives you like the long time average statistics for expansion and contraction in the system. So you can find a formula, which I'm sure we're not the only people to observe this, right? Someone must have written this down somewhere, but we couldn't find it in the literature. But essentially what you can prove is, there's a couple of classical identities for the Lyapunov exponents, but they each have a disadvantage. So we wanted to find a formula that worked really well, maybe specifically for SDEs. And so we found this formula, which essentially relates the Fisher information type quantity on this stationary density F to the Lyapunov exponents. And I know you're thinking this should be 1 instead of 2. Now, of course, if you like kind of add the formulas, you get the right thing. But then anyway, we're not going to use that. There is an analog. There's like a conditional Fisher information analog where you get the correct answer. Correct answer is n lambda 1 minus lambda sigma. But anyway, that formula is a little bit more complicated. So I just put the simple formula on the board. And so what's the advantage of this formula is that this is a positive quantity on something that depends only on the stationary measure. So the other two classical formulas fails in one of those two things. This has the nice properties of the other two classical formulas. They're all equivalent. It's the other classical formulas. So why is this useful? So if you think about small noise limits, then if you track where the nu goes, you basically get this. You get this Fisher information thingy is balanced by this thing divided by nu. So now you can kind of guess where this lambda 1 divided by nu going to infinity is going to come from. So you have that this Fisher information is equal to this ratio. And lambda sigma for the case of Navier-Stokes is like nu times the trace of your dissipation, which in finite dimensions is still just a fixed number. Oops. So we have like a number, we have lambda 1 divided by nu plus a number, minus a number. Oh, sorry, plus a number. Right. So now basically we're going to do some PDEs to link this formula to something we can understand. So the point is that this is just directions in some of the directions. This is just derivatives in some of the directions on the manifold. But there's an established theory in PDEs called hypoellipticity for how to relate derivatives in some directions to derivatives in all directions. So that requires some hypoellipticity condition, which has to do with, it's basically a generalization of ellipticity, which says that, okay, maybe your forcing directions don't span the tangent space, but if you start commuting everything and look at the Lie algebra generated by commuting all these vector fields, if that will span the tangent space eventually, then you're basically elliptic. You're basically as good as elliptic. So that is a condition that can be quite hard to check. So that's what Sam and I did, just check that condition for Navier-Stokes. But if it's true, then you can relate derivatives in some directions to derivatives in all directions. So in particular, you can prove the following PDE estimate. So it's important to understand this Kolmogorov equation depends on nu, but it's got a small parameter. And the solution depends on nu, but this functional identity does not depend on nu. So it says if you are kind of projective hypoelliptic, then there exists some number fixed independent of nu such that for every compact set, you get a constant that relates this Sobolev space regularity to the Fisher information. And it's just a purely PDE estimate. It uses some techniques. We use techniques based on Hormonder's original proof. It's kind of like an L1 version of Hormonder's proof, which Hormonder uses L2 duality in an important way. So a little bit of work to do, but it's doable. And once you have that, then you can see that somehow the Lyapunov exponent gap is directly related to the regularity of the projective stationary measure. So basically, we can prove a dichotomy, and somehow, I don't know. Last time I gave the talk, it was much faster. It's okay. you can prove a dichotomy that essentially says that either this ratio goes to infinity, or you can pass to some kind of limit and produce a stationary measure for the deterministic, like unforced, undamped projective process. And for reasons which are not obvious, that turns out to actually be not bad. But to have a deterministic invariant measure for your projective process like that, it's kind of like being in the isometry case of Furstenberg's theorem. It's not at all obvious. That's a kind of a highly non-trivial lemma, kind of like ergodic theory, dynamical systems lemma. But so basically, essentially, this latter condition is surprisingly easy to rule out. So if you have growth of the gradient on a positive measure set, then you know that this cannot happen, this B cannot happen. Now that can still be hard to verify, but it's a lot easier than verifying chaos. So for example, for Navier-Stokes and other similar models, it's actually easy to check. There's a special structure due to the, and basically if your nonlinearity is a polynomial, it's easy to check. A homogeneous polynomial, it's easy to check. Okay, I'm not going to talk about the attractor dimension estimates. That's if we ever get around to writing the papers. Then one thing that Sudan and I did was also just fill in kind of an obvious thing, which is if you are volume preserving, can this technique give you at least a little bit of quantitative information? So we know how to check that if your SDE, which is volume preserving, there are sufficient conditions for proving chaos. So basically what we prove is that if you then, but still looking at the small noise limit, that basically there's a gap. There's a kind of a gap between how unchaotic can you be? So can you make, if your noise is size nu, can you make a Lyapunov exponent that's nu squared? And the answer is no, general. So you either are rigidly zero, like rigidly non-chaotic, or you are at least like nu. So it's another kind of dichotomy, Furstenberg-like dichotomy. So it uses the previous kind of techniques as it builds on the previous kind of techniques.
Is it finite? That limit?
Finite. What?
That limit?
Oh, sorry. This is probably a limit. Yeah. But yeah. That's the limit. Oh, sorry. Is it finite? Yes. Yeah. So lambda 1 is bounded above by like. Sorry, what do you mean? No. Sorry. In general, it should be infinite.
Yeah.
Sorry, but it could be finite. So you can construct examples where lambda 1 scales like nu, but you just can't construct examples where it scales less than nu. Sorry, I didn't really understand. No, this limit could be infinite. Like the last example for Navier-Stokes. So maybe that example is a little bit too hard to explain. Let me explain another example. So one thing that what kind of direction we're going is, now if you think about this anomalous dissipation picture, I sort of use it to motivate a lot of things, but in finite dimensions, it's kind of there's no clear analog. So Andy, I don't know if it's really due to Andy, but Andy suggested this problem in his book, Andy Maida, where imagine studying a system that was like qualitatively like Navier-Stokes. So imagine this is a bilinear nonlinearity that satisfies some structures. Let's think of it as like the nonlinearity in the Euler equations, or in the Navier-Stokes equations. But now imagine that instead of damping every mode, I'm going to not damp some subset. So my damping operator is going to have a kernel. Then you don't know that there exists a stationary measure, because what if the energy just piles up in that kernel? So then under what conditions can you prove that you have a stationary measure, that solutions really on average stay bounded? So for example, think about the Navier-Stokes, but for some reason you just decide not to damp the sine 2x mode. Just like, meh.
Question.
Yes.
For the noise in that, would that be non-degenerate noise?
For this one?
Yes.
Yeah. You still. What do you mean by non-degenerate?
Full rank.
Oh, no, it doesn't really have to be full rank, but just imagine the noise is full rank. Yeah, just at least hypoelliptic. Yeah, no, I skipped some slides on non-hypoelliptic noise, but we can talk about that later if you're curious. Yeah. So just think about the noise full rank. So you're forcing every mode, in finite dimensions. So basically what's going to happen? So you have to rule out that energy doesn't pile up in the bad subspace. And I cannot say that Kyle and I really solved this problem because we did not really characterize it. But we set forth a method for characterizing it. And we were able to apply it to a couple of simple cases. So one simple case is when this bad set, the kernel of A, is not an invariant set, or contains no invariant sets for the deterministic dynamics. Then it's actually relatively easy to prove that there exists a stationary measure. Because, well, I'll explain what the intuition is. The next easiest case is, for example, if the bad set is one-dimensional, let's just say it's one-dimensional, and it's an equilibrium point for the deterministic dynamics, but it's unstable. It's an unstable equilibrium point. Then you can also prove that the energy can't pile up in that mode. We're working on a paper that's done, but sort of, kind of does much higher dimensional examples that are more general. But anyway, and the Kyle Liss paper has a list of kind of possibilities, including one or two possibilities with some non-trivial invariant sets inside the kernel. But essentially, you want to prove that any invariant sets in the kernel are somehow suitably unstable. So the proof basically goes on the following idea. It's a time averaged coercivity estimate. So this is the estimate that you have a bound on. This is bounded by like 12 on, the time average, this is like bounded by the size of the noise. This is the dissipation. What you don't know is if the dissipation bounds the norm squared, as it would if it was positive definite. So what we're able to prove is that if you pick time like 1 or whatever, that it's not true pointwise in time, but it is true on time average. So essentially what you're looking at is that anytime you go towards the bad set, you are ejected from the bad set sufficiently fast, roughly speaking. And you can basically reduce this kind of time average coercivity estimate to suitable estimates on the exit times from cones around the bad set. And then we use some SDE stuff to basically come up with a bunch of examples for which we can do that. Some non-trivial, some trivial, but yeah. We don't have a general theory for that, let's say. But I think that's all I'm gonna have time for, so that's it.
So are there questions or comments?
Let me ask a philosophical question. So what is the reason, because the noise you put is really weak, even you are only kind of forcing like a finite modes, and how come that makes things so much better than the deterministic problem?
I think the easiest way to see this, I think there's many levels of answer to this question. I think one of the easiest ways to see this, I think from a technical perspective, is if you think about basically this transport equation, right, is equivalent to the ODE. And whereas this whereas you may have instead whereas if you have noise, then the analog thing is this subparabolic piece.
Yes.
And if you are hypoelliptic, then solutions to this are still smoothing.
Okay, but this can be really weak smoothing.
Not really, actually. Like solutions to this will still be instantly, if you're hypoelliptic, really hypoelliptic.
Okay, okay,
And solutions to this will still be C infinity.
okay,
It's almost like you're elliptic.
okay.
Even if you only force like 10 modes. Now, when you send dimension to infinity, it becomes a little hazier. We don't really have a good understanding of infinite dimensional hypoellipticity. So that's definitely still in its infancy compared to the 5-dimensional case. But yet RDS is still much easier than deterministic dynamics even in infinite dimensions. So this is not really an answer. Peter probably has a better answer. It's not an answer. We can discuss ad nauseum about all the different answers. But this is one, and this property, the fact that noise is going to regularize your dynamics, regulate these kind of dynamics is one of the fundamental reasons why you have uniqueness of stationary measures.
Yes.
And once you have uniqueness of stationary measures, then you have, the ergodic theory tells you that the long-term dynamics of almost every initial condition is the same, which is, I think, a really powerful thing. And even more, these stationary measures, the unique stationary measure has some structure, has some reasonable structure. Whereas for deterministic dynamics, the only case we have this is when you have something like an SRB measure and things like that, and we don't know how to check that in any real system. So another thing is like, if you have a positive Lyapunov exponent in a random system, it's the closest thing to being uniformly hyperbolic, but not actually uniformly hyperbolic. Somehow it's somewhere in between the difficulty, but it's something like a non-uniformly hyperbolic system, heuristically, which is a really powerful place to be if you can't be kind of trivially uniformly hyperbolic. Yeah, I don't know if that makes sense. We talk more, trust me, I have more.
Other questions, comments?
So if you think about scalar drift diffusion equation, but with a non-divergence free flow, how much of the dynamics or like the results would carry out that?
Right. So we used the fact that it was divergence free to use the volume preserving structure. And so our technique using kind of going through this Furstenberg method would no longer work, no matter how much slight compressibility you had. Now, if the velocity field were evolving in a finite dimensional space, then you could use the second set of techniques that I presented, where you're allowed a little bit of compressibility. And then you could probably prove Lagrangian chaos in that case. But those methods we don't know how to extend those methods. Oh, no, sorry. Right, we don't know how to extend those methods when your velocity field is evolving in infinite dimensions, but it might be doable because, the Fisher information methods, just like the Furstenberg methods, you can do a partially infinite dimensional thing where the velocity field lives in infinite dimensions, but the ODE is still finite dimensional. That's kind of only half infinite dimensional, right? So we were able to make a kind of half infinite dimensional extension of Furstenberg. A truly half infinite dimensional extension of the Fisher information methods might be possible. There's some indication that it might be possible, but we don't know how to do it.
What if you add a deterministic force to the equations so that you would know that the attractor maybe has a dimension greater than 0? Does it get easier?
No, it doesn't really change.
Then you would
anything.
have the Lyapunov exponents for like the dynamical system, at least the deterministic one. You would know that they are.
Why would you know that? Why would you know that?
The existence, like, well, not all the time, but at least there are cases, let's say in the periodic case, where we know that there is the unstable manifold is non-trivial.
But only very specific examples, right?
For very specific.
Yeah. So in those very specific examples, then, I've never carried it out, but I think that you should be able to do, for example, I think it's kind of SDE, but then you have a fixed external forcing. And if you know that the fixed external forcing has a positive Lyapunov exponent, you should be able to prove like uniformly anew that you have positive Lyapunov exponents. That's it's a continuity theorem that I think should be possible to prove. But I'm mostly concerned in cases where you wouldn't know that about your underlying system. Yeah. So I should mention that there's a bunch of literature that I didn't go through in the talk, but is very important, which, for example, does a lot of work on this similar system where you get really precise answers for what lambda is. You get exact scaling laws in some cases, right? But to do that, you need to know, basically, you do that by getting really precise understanding of this projective stationary measure. So you get almost like asymptotic expansions for this form of the solution of this PDE. And it's pretty impressive that it can be done in the examples that it's done. But for something like Navier-Stokes, I don't think this will ever happen. So we will, never have a clear description of the projective stationary measure for Navier-Stokes. The sun will burn out before we have a complete description of this. So waiting around for us to have a total understanding of this. Yeah, anyway, so we specifically wanted to develop a technique that was robust enough to get basically a bad answer for many problems, as opposed to getting a really good answer for one problem. So if you apply our technique to some problems, it gets a completely bad answer that we know is bad, right? It proves chaos, sure, but it gets a really bad quantitative answer. But we were trying to develop a technique that was so agnostic as agnostic as possible to the underlying dynamics, where you need to know as little as possible. If that makes sense. Because we will never understand. The system we're interested in, we will never understand.
Other questions or comments? No? Igor?
No, just.
Oh, sorry. Okay, Igor is leading the applause.
Not sure. I was in the last, so. All the lectures.
Okay, yes.